Hey everybody, and welcome to the first of our first of our AP Physics 1 reviews. Today we're going to be looking at kinematics and Newton's laws and circular motion with gravitation, kind of a combination of those first two topics. We'll do kind of a review of topics first, and then we'll do some practice questions. And if at any point you have questions, by all means, interrupt me. Be rude about it because I don't notice every time. But folks who are online, we have nobody online. I don't know who I'm talking to. All right. Kinematics first. Kinematics is the word we use when we talk about just describing motion. We don't do any explanation for motion at this stage. But in order to explain motion, we have to have this really clearly defined motion. Sometimes we like to have it numerically defined, where we do calculations, sometimes graphically defined, sometimes pictorially defined. That's a word. So we started with a few different ways to represent that motion. Now, the PowerPoint that I'm going from, or actually Google Slides presentation, that's available online. I sent you a link to it like a couple hours ago, so don't feel like you need to write everything down here. But if you feel like making notes, I won't object too strongly. We had narratives, which was just describing motion in words. Motion diagrams, that was supposed to be like a strobe light picture of what was going on with our object. So when you travel a long distance, we had a big, or when you travel fast, we had a long distance between flashes of light. So those kinds of pictures. Graphs, we did mostly just position versus time and velocity versus time graphs for these. You could potentially have acceleration versus time, but those aren't very common. So no, not too worried about those ones. And then we went into the calculations. We had kinematics equations in one dimension, and then once we played around with vectors for a little bit, we did the same thing in 2 dimensions. So we'll just kind of go through a overview of the topics that we covered with those. A few things that I think you want to watch out for when you have these types of problems. But and obviously we can't relearn everything from a whole semester's worth of class. So don't think of this as a learning activity, more of a sparking your memory activity. Oh yeah, we did talk about that. I don't really remember that. I should go back and do some more work with that kind of thing. And then we will do some practice with this later on as well. Regardless of the type of description, whether it's a narrative or a motion diagram or a graph or an equation, we have certain types of information that we're trying to get out of here. So position, velocity, and acceleration are the big ones at this level. If you go into further levels, you can look at how acceleration changes over time. It's called the jerk, which is a fun function just because it's a nice word. You get to call people names when you calculate jerk. But for us, we'll mainly look at constant acceleration problems. Really, we can only calculate constant acceleration problems. So if we have something where acceleration changes, like the ball is falling due to gravity, but then it hits the ground, and instead of accelerating downward, it starts accelerating upward, we have to break that problem up into 2 separate constant acceleration problems. So we may have to divide these into different time intervals. In particular, whatever type of representation you're using, make sure you mention or draw or include in your graph any position that looks like it's significant. So if something hits the ground, that's usually significant. Gets up to the highest point, that's usually significant. Hello, who is it?
Hi.
Oh, hi, how you doing?
Good.
Well, welcome. We're just looking at so, they might mention, hey, how you doing? They might mention that you're looking for, what time it is or how much time has passed when they get to this location. So that'd be a significant location then. Anytime we have an object stop, that's probably some significant point. Anytime it changes directions, which you have to stop to do, can't go this way and then this way without stopping, that's probably a significant moment too. So those are ones to pay special attention to and make sure you're including in any type of representation. So take a minute, read through the narratives here. We've got lots of information in this paragraph, and we'll kind of debrief after you've read it. So again, we look for position, velocity, and acceleration, and statements that it changes after this amount of time. So we have the car starting from rest. That was one of those phrases to watch for. Doesn't say the speed is 0, but that's what it means. Starts from rest. At the top of a hill, so that's a position statement. Begins to roll and accelerate, so acceleration statement there. Downhill. Reaches a speed of 10 miles per hour, so that's a velocity statement after 4 seconds. That's a time statement. Rolling before reaching a flat point at the bottom of the hill. And then it coasts, accelerating in the opposite direction. So it's moving one way, but accelerating the other way. That means it slows down. Accelerating the opposite direction at 0.5 miles per hour per second, which is kind of a weird unit. For this class, we got used to meters per second, meters per second squared. And then traveling another 140 feet, again, weird unit for physics. We use meters, not feet for the most part. Before stopping, and so that's another velocity statement there. The stopping tells us velocity is 0. So this is just a written account of motion. Your English teacher probably wouldn't approve of how this is written because it's really repetitive and redundant, and it says the same thing multiple times. Love redundancy jokes. Love them. Department of Redundancy Department. That was one of my favorite jokes when I was there. So it's all right, though. We're not writing an English essay. We're writing a physics essay, I guess. So we want as much information, even if it's a little repetitive, we want that information present. We don't want our audience to have to guess at what we do and do not understand about the situation. So when in doubt, go ahead and include the same thing twice in different forms. That's fine. Say something has an acceleration of 0 and that it's traveling at constant speed. Why not? Why not? Two things that people get tripped up on here: accelerates at versus accelerates to. Those phrases don't mean the same thing. Now, the units that go with the number that they would have right after this, that'll be a clue as to what type of measurement they're giving you. That's true in general. The units are always going to be clues about what type of measurement it is. When something accelerates at, and then they give you some number, that number is the acceleration. When they give you accelerates to, and then a number, that's the speed or the velocity that it gets to at the end of its acceleration. So if it accelerates to 25 miles per hour or 15 meters per second or whatever, that goes in for final velocity, not for acceleration. Very close in terms of the wording, but very different in terms of meaning. But if they were saying accelerates at, they'd have to give you 5 meters per second squared, not 5 meters per second. So use the units, they're good clues. From rest, or comes to a stop, or changes direction. I don't know why I don't have those ones in here, but those all mean speed is 0 at that moment. At its highest point, or maximum height, that means the object was moving upward, it's about to start moving downward, but for that one instant, it's not moving up or down. So the y velocity, at least, is 0. If we have an object that's kind of going on a parabola, so like a projectile motion type problem, we can still have x motion, but our y motion has to stop for just that instant. It gets to its highest point. Questions about the narratives? Okay, I see a few people taking down some notes on the things to watch for. I'll give you a second to do that.
Accelerates at means that's acceleration, right? And then accelerates to velocity, the
Yep, exactly. Any others? Okay. If you joined us recently, I said this once before, but the PowerPoint that I'm working from, I sent a link to that and the other things we're going to be using in class today to you. So if you don't get everything down, you've got it electronically at least. Motion diagrams are our next topic. Again, these are supposed to be like diagrams you can bark.
Sorry.
Oh, they just want love. Well, last time it was my cats making all the noise, so it's just a change now. With the motion diagrams, we see the position just as where we draw this dot. We see multiple moments in time on the same picture, which is sometimes a little difficult to wrap your head around. So I think that strobe light idea is nice. We see one flash, and this is what our object is. Next flash is here, the next flash here. We often include arrows to show either the velocity or the acceleration, or sometimes both, for the motion diagrams. So it looks like here the red arrows represent the velocity, so that's the direction it's going to move. This arrow will point to the location, to the next location of the object, basically anyway, unless we have really, really rapid acceleration. So from here, I'm going to go up and to the right, and I get here. From here, I go up and to the right. Ooh, that arrow is a little smaller, though. Remember, with motion diagrams, the size of the velocity arrows indicates how fast we're going. So as this thing gets up higher, it's slowing down as well. Now, the other thing I noticed about these arrows is this one is a lot of up and just a little bit to the right. But as we get up here, well, we've got just a little bit to the right, but even less going upward. So our velocity in the right and the left direction doesn't look like it's changing in this picture, but in the up and down direction, it definitely is. So it's a little right every time. It starts with a lot of upward velocity, and then a little upward velocity, and then up top, no upward velocity, and then a little downward velocity, and then more and more downward velocity until we have a lot of downward velocity over here. If only the up and down velocity is changing, we know your acceleration must be either up or down. Here, our y velocity starts positive and then gets to 0 and then gets to negative, so we know that our y velocity is negative or downward also. So that's the purple arrows here showing constant acceleration downward. Now, I don't know if it was intended this way, but this definitely could represent a projectile being thrown through the air. We typically assume that there's no air resistance, so we don't slow down in the x-y direction, or in the x direction. We don't speed up in the x direction either. All we have affecting our object is gravity, which pulls things downward. So with motion diagrams, oh, that's the same things I was just saying. Okay, well, here's a point I didn't mention. The acceleration on these pictures sometimes is tough to figure out how big or how rapidly we're accelerating. So in general, we don't really worry too much about the size of the acceleration vector arrows, just the direction for them. The velocity ones, though, we should be able to tell on those. Now, I think I mentioned this a minute ago. If an object is going fast, then it's going to travel a big distance between subsequent flashes of light. So we should show big distance in position, or a big difference in positions for those. If it's going slow, we should see small difference in positions. If it's speeding up or slowing down, we should see the distance between those dots either increase or decrease. Speeding up and slowing down or changing directions, those are things we want to focus on for all of these different representations. On these diagrams, if it changes directions, sometimes that's not a big deal here because we can have our velocity arrows changing direction. But if instead I was throwing that thing straight upward and then it came straight back down, we had that situation where we'd end up drawing one row of dots and the next row of dots right on top of it. So it's completely acceptable to draw a new line of those dots over here. So it goes up and then, whoop, let's pretend that, that this row is right on top of the other one, and then it goes back down. So you'll see that sometimes also. All right, incomplete diagrams. You'll definitely see some of these on the AP test. They may or may not give you everything that we've just seen on the last diagrams. They might not give you velocity. They might not give you acceleration. Maybe they won't give you either of those things. Maybe they just have the dots and like number them. So this is the first dot, and then it's here, number 2, and then it's here, number 3. You can infer quite a bit just from the locations of the dots, whether the object is speeding up or slowing down, whether it's turning or going straight, whether it changes direction. All those things we can get just from where the dots are. One other thing to watch for here, if we're speeding up, and we do have those arrows on our diagram, the velocity and the acceleration are in the same direction. So the arrow should be pointing the same way. If it's slowing down, velocity and acceleration are in opposite directions. The arrow should be pointing the opposite way from each other. I think that's all for motion diagrams. Yep. Questions on those? How are the dogs, Katie?
Poorly trained.
Okay. Graphs of motion next. 3 types that we might deal with. Probably won't have to do anything with the acceleration graphs, but we could. I mean, there's no reason not to. But the position versus time, sometimes called the distance or displacement versus time graph, that's this one. So you have x over t. It's a little tough to read from where you are probably. And then velocity versus time, that's v versus t. Those are definitely things you'll be expected to either read or to make on the exam. Maybe some of each. So with each graph, we had kind of a different set of rules to pay attention to. The first rule, though, that you absolutely have to pay attention to is read what's on the y-axis. I'd say more than half the mistakes I see in class on these things are interpreting this graph like it's a position graph instead of a velocity graph. So if you misinterpret this one, you might say, oh, the object starts at this position of 12, and then it gets closer and closer to a position of 0, and then it goes to the negative position. And that's not what's shown here at all. It's a velocity that's going from 12 to 0 and then negative. So read what's on the y-axis. Big step. Now some general things we can look at for these are going to be the y value. So read what's on the axis to figure that out, what the y value means. The slope of the graph, or the area underneath that graph, area under that curve, which these 2 things really are simple versions of calculus things. So if you're doing any calculus, you have seen lots and lots of this stuff, just in a more difficult form than what we do. So on the position graph, if you forget what the meanings for the slopes are, it's pretty easy to figure out just based on units. The y-axis will have units of meters, and the x-axis is going to have units of seconds, or some distance unit and some time unit. If we did the slope, that's y over x, that'd be the y units over the x units. So meters over seconds. I remember meters per second, that's speed. Same thing for velocity versus time. Y-axis is meters per second, x-axis is seconds. So y over x would be meters per second per second. Acceleration, bam. You can do the same thing for the area under the curve. We have a velocity graph, and we make like a triangle on the velocity graph. We do our area under the curve, so area of a triangle, 1/2 base times height. That base measurement, so like the x measurement, that'll be in seconds. The y measurements in meters per second times seconds gives us meters. Displacement, distance. Use the units. Know the units really well, so that's something just definitely to memorize. These units go with this quantity. And then use those to help you figure out anything that you forget as far as what these relationships are or what type of information they're giving you. So for a summary here, we don't ever have to do anything with the area under a curve for a position versus time graph. we thought about units on that one, that'd be meters times seconds, which isn't a quantity that we have done anything with. But the slope will be the velocity. The y value is the position. For a velocity graph, we just talked about area under the curve is change in position. Slope of that will be meters per second, so acceleration. The y value on a velocity graph is velocity, of course. And for acceleration, the y value is acceleration. The slope, we don't want to do anything with here. It's called the jerk, the change in acceleration over change in time. And then the area under that curve would be the change in velocity. I won't go through all of these. I just wanted to show you that these are here. You don't actually have to memorize any of this stuff. It all just follows from knowing the stuff that was on the previous slide. But things like here, like we have zero slope on a position graph, that would mean that we have zero velocity. Well, the slope means velocity, so if the slope is zero, yeah, the velocity is zero, it stops. There are some key features to the graph and what they mean for each of these different graph types, so that wouldn't be a bad thing to review at some point here. But again, nothing to memorize, it just all follows from knowing what the slope means and what the area under the curve means for each graph. Questions about graphs before we move on to the equations?
Is that all on the review PowerPoint?
It is, yep, it sure is. All right, our first equations. By the by, if you don't have an equation sheet, you can print one off from our website, from bennettscience.com. Actually, I have extras here too if anyone who's here right now doesn't have one. Thought I had extras. I do. Anybody need one? I thought for sure these would be framed on your wall.
That's why it's at home.
Oh, right. On the wall. No? You need one?
No, good.
Okay. So the equation sheets for the AP exam, they do have all these equations on them. I would spend some time reviewing just the equations, making sure that you remember kind of the sorts of problems where you would use each one of these equations. Kinematics, we can use anytime we have motion and we want to relate these kinematics quantities, position and velocity and acceleration and time. When we use these equations, we either have to have constant acceleration or we have to have a value for the average acceleration to plug in here, or we'd be calculating the average acceleration. So if acceleration is changing, these don't work for us anymore. These are all derived with that assumption. Throw out the assumption, and you have to throw out the equation. So, now, you won't have to do any kinematics problems where the acceleration is changing continuously, but like I said, you may have to break it up into two different stages.
Brianna, do you have truck?
So just be aware of that anyway.
Yeah, I think so.
Sheets, so I need to recopy those, of course. We'll come back to some practice with the kinematics equation stuff. For vectors, the big thing we did with these was add vectors together. Adding vectors isn't the same as just adding numbers. We have 10 miles to the north and then 5 miles to the east. It's not just 15 miles northeast. We have to do the triangle stuff, make a right triangle. So we go north and then we go east, and then our overall vector is a diagonal. It's the hypotenuse of that triangle. We like right triangles because we can use, well, okay, maybe you don't like right triangles. Maybe you hate right triangles with a passion at this point in your lives. But if we want to be able to calculate things, we like right triangles because we can use sine, cosine, and tangent. We can use the Pythagorean theorem. There are other relationships like the law of sines and law of cosines you can use if you have a triangle that's not a right triangle, but we have a 4 or a 5 or a 6 vector problem. We're adding all these different vectors together. You can't use law of sines and law of cosines on something other than a triangle. So the general procedure on these things for adding vectors, no matter how many vectors we have and how many different directions they're in, is we do that vector resolution process. We take each vector and say, well, this one is pointing up into the, sorry, I can't do this backward, up and to the right. So how much to the right is it going and how much up is it going? We find the x and y components of that vector. And for however many vectors we have, we'll just add all the x's together, and that's going to be overall how far in the x direction do we go. We add all the y parts together. That's overall how far in the y direction do we go. And then we can make a new right triangle this time that has the x component horizontal and the y component vertical, and then we can draw on a diagonal there, draw on a hypotenuse and solve for that value. Oftentimes we'll have to solve for an angle for that as well. Practice on that to come as well. When you add vectors, there's a term that you probably ought to know with these. The resultant is the answer to a vector addition problem, just like the sum is the answer to a scalar addition problem. That's resultant. So sometimes they'll phrase things like, what's the resultant velocity or what's the resultant force? That's just taking a couple of vectors or maybe a lot of vectors and then doing this vector addition process. Questions there? Fantastic. Now that we've done kinematics and we've done vectors, we can combine those two and look at vector motion or two-dimensional motion. Not vector motion, vector kinematics is the name for this. Two-dimensional motion, you could actually do three-dimensional motion or four-dimensional, any number of dimensions as long as they're perpendicular to each other, which is tough after three, the way we experience the universe anyway, but whatever. Fortunately, though, we don't have to do anything beyond two-dimensional problems at this level because they're kind of a pain in the neck. So save that for college-level physics or a few years down the line anyway. With 2D motion, we have to work in only the x direction or only the y direction for any given calculation to do. So we don't want to mix and match variables. If you've got some horizontal speed, you're not going to use acceleration as 9.8 meters per second squared downward in that calculation. Yeah, it probably, if it's a projectile, yeah, it's accelerating down at that rate, but that has to be paired up with y velocities and y displacements. Time is the only thing that doesn't have a direction with it in the kinematics equations. Time is a scalar quantity. So we can use it with the x stuff, and we can use it with the y stuff. As a result, almost every problem that they set up for you on the kinematics stuff, they'll give you enough information on either the x side or the y side to solve for time, and then you have to use that time on the other side of the bridge there. So find time using the y stuff, and then use that time to find something in the x direction. Lots and lots of problems like that. I think it makes a lot of sense to start getting organized well on these problems. We end up with 11 variables to keep track of on these two-dimensional motion problems. It can really easily get messy on these problems. I like to divide things up by x's and y's. That helps me to remember, oh, I don't want to take this value and use it with this acceleration here. Don't want to mix and match x and y stuff. However you set it up, make sure that you're setting things up in a way that makes sense for you, that's going to help you keep track of what things you can use together and what things need to be separated. Now the variables are the same for x and y, just all the x's get replaced with y's for subscripts or for the big letters. Your green sheets, your equation sheets, have all the equations listed with x variables, but you can just plug in y's instead, and they're still the same equations. Be careful of signs when you're doing these ones. Think about which way am I calling positive and which way am I calling negative. And every number that you put in here, be aware of what sign it should be. If you're saying up is positive and down is negative, then acceleration due to gravity should be a negative 9.8 meters per second squared. You don't have to say down is negative, though. You might have a problem where it makes more sense to make down be positive and up be negative. You get to choose on these ones. So just be consistent. Same with right and left. Questions on those? On the given information stuff. Okay. Those equations are used for two-dimensional motion in general, but the application that we usually use with these is for projectile motion. So an object that's moving through the air, and it's subject to acceleration from gravity, but typically not from anything else. So we don't have, rocket boosters, and we don't have large air resistance or wind blowing this thing off course. So typically we're going to see acceleration in the x is 0, and the y is at 9.8 meters per second squared downward. Since acceleration in the x is 0, the velocity in the x direction is constant, which means in those equations we get a lot of terms that cancel out for the x direction on the projectile stuff. So let me flip back to that for just a second here. So here, if acceleration is 0, we're left with final velocity equals initial velocity. All right, we know. If we put acceleration as 0 here, we get final velocity squared equals initial velocity squared. Square root both sides, and we get final velocity equals initial velocity. Yeah, we know. Up here, this is the only equation that we're really going to use in the x direction, because it's the only one that doesn't just tell us velocity is constant. So in this one, this term drops out, and we're left with still something meaningful there. Now you can rearrange that equation. If you move this x naught over to this side, we get x minus x naught equals v naught t. Divide both sides by time, and we get basically distance divided by time equals speed, which is an equation that you're probably familiar with from outside of this class as well. Especially if you've done a long road trip. I do that calculation about every other minute when I'm doing a road trip. And they're 250 miles, and I'm going 65 miles per hour. Okay, too long. Time for another audiobook. Hey, I just said that. Go me. Now, like I said, most of what you do with two-dimensional motion is going to be projectiles, but don't assume it is unless they give you the information to tell you that it is. Something's thrown through the air, yeah, projectile. Something's thrown through the air and blown by the wind, projectile, but now we have acceleration in the x direction probably. Or a plane moving through the air, not a projectile. Hopefully not a projectile. You don't want to be on the plane if it's behaving like a projectile. So we could have acceleration in the x direction, we could have acceleration in the y direction, or maybe it's got constant velocity and we don't have acceleration in either direction. So just be aware of those things. If they don't give you the information to know that it's a projectile, then we shouldn't start with the assumption that acceleration is 0 or 9.8 for the x and y directions respectively. Things to watch for with projectiles. If they say something is launched horizontally, that means it's not launched upward, not launched downward, not even a little bit. So it's launched this way, not this way, and not this way. If we take that velocity and break it into its components, it doesn't have any upward or downward component to it, at least for the first instant. So our first instant y velocity, our initial y velocity, is 0. This says Vx naught is 0, and that's wrong, so I need to fix that. Make sure you don't write it down incorrectly there. That should be Vy naught equals 0. If something, even if it's moving in 2 dimensions, gets to its highest point, that again means it was moving upward. Might be moving horizontally too. But it was moving upward. It's about to start moving downward. In between those, we have to stop in the y direction. So Vy is 0 when something is at its highest point. Now they may not state it that way. They may just say something like, how high does the ball get as it flies? So you'd have to recognize, I need to look at this last moment being when the thing is at its highest point. And then that change in y position, that's going to be how high it gets, and my velocity at that point is going to be 0. If something's launched at an angle, so we're not kicking the stone horizontally off the cliff, we're launching it at some angle off the cliff. Well, we need to figure out how fast it's moving horizontally and how fast it's moving vertically. That's vector resolution again. And then those are the quantities that go into that table of given information, starting x and y velocities. And then if something starts and ends at the same height, then our initial and final y position would be the same. Since we get to choose our axes, it typically will make sense just to make those both be zeros. If it's already been chosen for you, that's fine. And we'll balance out on the equations. So you get 15 meters equals 15 meters plus starting velocity times time is 1/2 at squared. To subtract the 15 meters on both sides, you get 0 and 0. They probably won't say necessarily it starts and ends at the same height. So you have to pay attention to the type of problem that we're dealing with. If something is like kicked off the ground and then it lands on the ground, they might just ask you, how long is the thing in the air? Well, it's in the air for the time between the moment when it was kicked off the ground and the moment when it hits the ground. It starts and ends at the ground. So let's make y naught and y 0. Y naught and y 0. Questions there? All right, shake it off. We're a third of the way through. Well, I guess we can kind of get started even without the PDF if we need to. I know a couple of things about Newton's laws just off the top of my head, like 1 or 2. Oh. The pinwheel stopped. I don't know. We'll find out in a moment. Yeah. Okay, I can just talk. Newton's first law, actually really all of, the second one's usually written pretty well. The first and the third law, I think, are typically written in really confusing ways. The first law says an object at rest tends to remain at rest, an object in motion tends to remain in motion unless acted on by an unbalanced force. And I don't like a couple of things about that. First off, the word tends suggests to me that sometimes it doesn't happen that way. Sometimes we have an object at rest and it just wanders off. No forces involved, just moves of its own accord. It tends to remain at rest, but not always. Okay, that's not how it works. It always remains at rest unless acted on by an unbalanced force. The object in motion, not only does it stay in motion, again, always, not just tends to, always stays in motion unless unless acted on by an unbalanced force. That motion is constant. Not just the fact that there is motion, but the quality of that motion too. The speed and direction of that motion is constant. Well, we've got a title. That's really all we need.
So when you cut it out, can you keep the wow part?
Wow! Just
wow.
edit out, edit out, edit out. Wow! Edit out, edit out. Yeah. A few years ago, somebody, I guess it was last year, we were making the canon. Somebody was taking a video while we were trying to put this thing together at the end of the year. And we finally got the thing working, and it makes this ridiculously loud noise. It sounds like a gunshot going off. Fires this tennis ball right through a sheet of card, or a ping pong ball through a sheet of cardboard. Makes this really loud bang, and it bounces around like crazy. And I'm just like staring at it, and I go, "Wow!" And someone was recording the whole thing, so that got passed around for a while at the end of the school year, just like that 1 sec. Not the, "Hey, check out this awesome vacuum cannon we made." Just listen how goofy Mr. Bennett sounds. Wow! 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 Again and again. Thanks, guys. Appreciate it. You and the love. So this is the phrasing that I like better for Newton's first law. Objects maintain constant velocity unless they're being acted on by unbalanced, and here's an extra word for us, external forces. Outside forces, we use that term sometimes too. It means the same thing. Unbalanced external forces. Now, once we get to Newton's second law, that talks about acceleration and force and mass, we find that we don't actually need this law anymore. The second law describes the same thing. So we'll come back to that. Unbalanced doesn't mean crazy. Man, those forces are really unbalanced. Just that they're not the same size in opposite directions. Right? Think about tug of war. We look at some spot in the middle of the rope. If there's an equal size force going this way and this way, that thing stays right where it is. Or if it's moving, it keeps moving at a constant velocity. We have to apply an unbalanced force to stop it from moving as well. External means from outside of whatever we've defined our system to be. Our system doesn't move unless it has an unbalanced external force. So systems could be collections of objects as we would typically think of them. So like you and I were all standing on the Earth. It doesn't really make a lot of sense if we're talking about our orbital motion to distinguish us from the Earth. We're pretty much moving the same way the Earth does. It's a good idea to treat us just as part of the Earth. But if I'm jumping from a high height and falling toward the Earth, then it's important that me and the Earth, we are separate. Though if I'm jumping from a high enough height, that won't last very long. Systems can be very simple things too. Something like a tennis ball is really a system. It's not just a single object because it's made up of lots of smaller pieces, atoms, molecules, bonded together. The atoms are made up of smaller pieces still, protons and neutrons and electrons. Protons and neutrons are made up of smaller pieces also, quarks. Now, we don't need to consider the forces between every single proton and neutron and electron to understand the motion of a tennis ball. We just need to know, gravity is pulling the whole thing downward, where a person is applying a force to throw it forward. I throw tennis balls like shot puts. Make sure I'm on camera for this. I throw a tennis ball. So we only look at those outside forces, the forces that are coming from objects outside of our system. We don't have to consider all the intermolecular bonds within the tennis ball to predict how it's going to move when a force acts on it. The second law makes the first law basically useless. If we plug in some combination of forces for our net force that is balanced, or there's no forces whatsoever, our net force, that's the vector sum of our forces, you can also read it as the resultant force, is 0, so that means acceleration is 0 as well. When force is 0, acceleration is 0, which means that whatever velocity that thing has, it keeps that velocity, which is the same thing that the first law said. But we also get this information about what if it's not 0? What if forces aren't balanced? Then what does it do? Well, it accelerates at a rate that's equal to how much of an imbalance we have in those forces, net force, the resultant force, the vector sum of our forces, divided by the mass of the object, or the mass of our system. We rarely are asked to solve for net force or for resultant force. More often we'll be asked to solve for a single force out of several that acts on an object. So if you think back to how we use this equation, usually our next step after we used this form of the equation, we didn't write the net force in there usually. Our next step after this was we replaced the sigma F with just all the different types of forces that were present in that situation added together. We also break that up into x and y pieces just like we did for kinematics. So acceleration in the x equals the total of all the forces in the x divided by the mass, and same for the y. So you often did this problem, or this equation twice, once for x and once for y. You could do it multiple, or even more than 2 times if you change your coordinate system. So maybe we're looking at circular motion. For a little while we want to look at x and y, but then we're going around in a circle, and our circle is like this. So maybe if we're right here, we want to look in the centripetal direction up toward the center of the circle, something like that. So you could do this equation lots of times for a single problem, and just look at a different dimension each time. And then the third law. This is the one that Oprah annoys me with, at least in theory. I don't actually know that Oprah has said any of this. It's just something I heard from another physics teacher a while back. Oprah talks about the third law like it's karma. A person helps out in their community, and then when something bad happens to them, the community helps them out. It's action-reaction. It's Newton's third law. You're not getting a car. Action-reaction is, again, kind of poorly labeled or named. So I think the word reaction has meaning for us already other than what it means in the third law. Reaction, we think of something happening after something else. The action happens, and then we react to it. There are subsequent events. The third law, though, is talking about forces that occur simultaneously. One force we call the action force, one force we call the reaction force. The reaction isn't caused by the action isn't caused by the reaction. They just happen at the same time. I don't know where action and reaction fits into this, why those terms are used. Newton's third law pair would be maybe a better term for that. Sometimes they say find the action-reaction pair. It's called Newton's third law pair, though. Third law just says when 2 objects interact, they each experience a force. Those forces are equal in size and opposite in direction and happen at the same time. They have the same duration, they start at the same time, and they end at the same time. I was walking to the park with my wife and daughter last night, pushing the stroller. Gwen likes to walk to the park now, but it was getting late, so we wanted to go fast. So we had the stroller, and for no particular reason, my wife was walking next to me. I veered over and rammed her off the sidewalk. And she said, this actually happened, by the way, just to give you an insight into how dorky I am outside of school, too. She said, hey, why'd you run into me? I said, well, I mean, there was a collision. Let's just say that. We collided. She said, what's this we business? You collided with, yeah, with you. We were 2 objects. We were interacting. We both experienced a force. They were equal in size and opposite in direction, hon. It didn't help my case any, but I brought it up. She laughed eventually after she shoved me into a puddle. So everything's forgiven. It's fine. These 4 forces are going to appear in the majority, or some combination of these forces will appear in the majority of the problems that we work. So they may not explicitly say this object has a gravitational force acting on it. We need to be able to tell, yeah, gravity, that's part of this problem. Gravity we can calculate. We're close to the surface of the Earth. We just do m times lowercase g, that was the 9.8 meters per second squared. m is the mass of the object. If we're farther away, like really far, orbit distance, or farther away, there's another equation for force of gravity. It's the capital G times m1 times m2 divided by distance between the objects squared. Just happens that if you're close to the Earth, then most of those terms equal 9.8 when you're near the Earth. That gravitational force is always going to act, it says toward the center of the Earth. I think just about every problem we do will be on Earth, but if we're on some other planet or moon, then it'll be toward the center of that thing. Toward the center of the other object, we're interacting with the other object. Right now, you and I are all interacting with the Earth, so the force we get is toward the center of the Earth. Third law, remember, says that the Earth gets that same size force toward the center of you. But it's a lot bigger, so we don't notice the Earth falling up toward us whenever we jump. Normal force is really just electrons in one thing repelling the electrons in another thing. We call this a contact force. When you lean up against a wall or stand against a floor or throw something up at the ceiling, well, anytime it contacts a surface and doesn't pass through that surface, doesn't do that ghost trick thing, we know that there's some force that prevents it from doing that. We call that a normal force. Normal in geometry means perpendicular. So this isn't like, it's just the ordinary average force here. Not that kind of normal. It's the perpendicular force. It's perpendicular to the surface. So if you're in contact with the floor right now, the floor is horizontal, the normal force is upward. If you're touching the wall, the wall is vertical, the normal force is out away from the wall. Friction is another contact force. You don't have friction with the floor unless you're touching the floor. This one, though, is going to be parallel to the surface. It tries to prevent these two surfaces from sliding past each other. So if you run and slide on the ice, that thankfully is finally gone outside. If you run and slide on the ice, there's a frictional force acting on you trying to keep you from sliding on the ice. It's not a very big one, though, so it takes a little while for that force to bring you to rest. If you ran out today and tried to slide across the concrete, wear knee pads, because it'll stop you darn fast. Lots of friction. If I'm trying to slide in this direction, friction acts back the opposite direction. Now, right now, I'm standing on the floor and my feet aren't slipping out from under me doing the stepping on a banana peel cartoon thing, because there is frictional force even when you don't have motion. We talked about the distinction between static friction and kinetic friction. Static friction happens between two objects that, without that friction, they would start to slide past each other. So it keeps them from starting that motion. But again, it's really just all about electrons interacting with electrons. We've got little bumps and grooves on both surfaces, and they catch on each other. And there's this repulsive force between the electrons in the bump of one surface and the electrons in the groove of the other surface. They keep each other from sliding past each other. Use your fingers like this as kind of an analogy. If you let those things settle down, they really get in there, and it takes a lot of force to free yourself. Really what you're doing on the surface is breaking off pieces of the surface, which is why sandpaper works. You break off pieces of the wood when you use the sandpaper, just because there's a lot of friction. Questions on that? Oh, tension. Tension, one more. Tension is the name of the force that we give to ropes and cables. We did a Tarzan problem. He was swinging across on a vine. We said there's tension in there. Tension force is along the direction of the rope. So if I lasso somebody who's standing over here, they would probably be very confused. Are you lassoing me? But once I have them lassoed, I can pull them toward me. I can't push them away from me. And I can't make them move that way or lift them up to the ceiling unless I move where I'm standing. If I want to pull them that way, I need to be on that side of them, because tension is only a pulling force in the direction of the rope. I can lift them up, but I gotta, throw my rope over a pulley that I have hidden in the ceiling for just such an occasion. How crazy would it be if I hit a remote right now and the pulley just like popped out? I wasn't lying, I told you. the remains of some student hanging up there. Oh no, I forgot about him. You guys have seen my bed of nails, right? No? Oh. Get that out at some point. That's just sitting in the back room right now, though. I had a student working in there on the test the other day, and she walked in, and there's a bed of nails on the floor back there. It's just a physics demonstration. Don't worry about like the safety of students who go in the back room or anything. All right. All these forces that are acting on an object act in some direction. Sometimes we have lots of forces in lots of different directions. So to model this, we use free body diagrams. Really, anytime you have a problem with forces on it, it's helpful to draw a free body diagram. Even if it doesn't specifically say, draw a free body diagram. I would say, for sure, if you're going to use the Newton's second law equation, acceleration equals net force over mass, start with a free body diagram. That way, when you get to the part where you have to put a positive or a negative sign with your forces, you can see on your picture, this force was over this way and this force is over that way. And I said this way is positive and this way is negative, so make this one a positive number and that one a negative number. It's also really helpful if you're not just going to use X and Y direction stuff for your directions. Like on the ramp, we often found it more useful to treat the x-axis like it was parallel to the ramp and the y as being perpendicular. When we did that, we made it so it only accelerates in one dimension. It travels along the surface of the ramp, so it wasn't accelerating in the y direction, which means we don't have to worry about displacement or velocity or acceleration in the y direction, only in one dimension, only in the x. So your diagrams are a good place to establish those systems that you're going to use, and to remind yourself that, hey, I'm not looking horizontal and vertical in this problem, or that you are doing horizontal and vertical. The convention that they've asked people to do for free body diagrams on the AP test is, in general, to treat your object like a dot. The only time we don't treat our object like a dot is, we got to this later on in the course, when we had things that rotate. We had torque on an object, so we needed to see where on the object that force acted. So if you apply a force at a spot, say close to the fulcrum of a lever, that causes some amount of torque. But if we go farther away from the fulcrum, that'll cause a different amount of torque, a larger torque. So for those problems, we actually tried to draw the object kind of looking like the object. They pick simple things like bars and pipes for those types of problems. But for something like this, where we're just looking at how the whole object moves through space, not how it rotates, but how it translates, just draw it as a dot. And then all of your arrows, like they are in this picture, they start at your dot. This one actually isn't a great example because the arrows should start right at the dot. We shouldn't have this gap here. They start at the dot and point away from it. So don't draw any arrows pointing in toward the dot. Just a convention they've asked us to use for the AP test. And then the last thing on free body diagrams, if we had some force that was off at an angle like here, like this, don't draw the components of that force on your free body diagram. Just draw the overall force. Draw on this, but not the x part and the y part of that force. At least not on the part where they ask you to draw the free body diagram. You can do that later on. The idea that we talked about was having like a pretty free body diagram and a working free body diagram. That's fine. Now, they're not trying to trick you with that. They will say right in the directions. If you need to add anything to your diagram, just make a new diagram for the next step. So they'll remind you about that. With forces, third law is an easy thing to forget about. Let's say we're drawing two objects, the free body diagrams for two objects that are interacting, maybe by a frictional force, maybe by tension from a rope in between them. It's really easy to put that force on one object but forget to put it on the other one. So if you're drawing multiple free body diagrams, do a quick check for third law pairs. We have one block sliding across the top of another one. They each get a frictional force from that interaction. They each get a normal force from that interaction. Forces are equal in size and opposite in direction also, so we might be able to use numbers with that later on. Don't invent forces. I see a lot of this, especially places where people will say, well, the object is moving this way, so there must be a force going this way. I don't know what to call that force or what's causing it, but hey, it's moving that way, so we better have a force that way. We don't have to have a force going this way for our object to move this way. If I give an object a push and then just take my hands off and let it go, it keeps moving that way, even though there's no force in that direction on it. So a good rule of thumb here is if you can't name that force, or even more specifically, if you can't name the object that it's interacting with to cause that force, it probably doesn't exist. You're probably making something up there. If you add a force to these problems that isn't really there, you've just created an impossible problem to solve. So this is a big deal for sure. We have a lot of problems where acceleration ends up being 0, but don't start with that assumption. In fact, we're never going to assume that acceleration is 0. We evaluate the situation and determine whether it makes sense to say acceleration is 0. If the object is sliding along the ground, it may or may not be accelerating in the x direction horizontally. But since it's not moving in the y direction, it's not going up, it's not going down, and the next moment it's still not going up and still not going down, and the next moment it's still not going up and still not going down, we know that not only do we have 0 velocity in the y direction, but the velocity stays 0 in the y direction, which means there's no change in velocity in the y direction, which means no acceleration in the y direction. Think through that process before you write down acceleration equals 0. Questions on any of those? Okay. Systems. We talked about it a little bit already. The idea, though, is just a system is a collection of objects. Sometimes it makes sense to group objects together, especially if they're going to move together. It might make sense to group them together. Person riding on a skateboard, most of the time, yeah, I would say treat the person and the skateboard like they were one big object. If you know the mass of each of them, just add them together. That's the mass of our one big object, our person skateboard system. If the person, though, you know, Biff said this skateboard slides out from underneath them, it probably makes sense to stop treating them like a system and then start paying attention to the mass of the person and the mass of the skateboard and the velocity and acceleration of the person and the velocity and the acceleration of the skateboard. Now they're interacting by this force that's pushing them apart from each other. So we can start considering that force as well. We only look at external forces on our systems. So if we're trying to calculate the force between the bat and the baseball, we can't make the bat and the baseball into a system. So that's an internal force there. It's between objects within our system. So we have to treat the bat like a separate object from the ball. And that one's pretty obvious, but you know, some of these that won't necessarily be the case. Say we have an object that, like a block with a rope attached to it, and then there's another block attached to the other end of the rope. We're pulling one block. If we're looking for the acceleration of these things, yeah, group them together. That's great. Look at the force I'm using to pull the two-block system, and that's the only force that's outside of the system. But if we're looking for the tension, that's a force between the two blocks. So we can't treat them like one object, because that'd be an internal force. So we have to separate them. Forces on this object, forces on this object, mass of this object, mass of this object, all that gets separated. Questions about systems? All right. Circular motion and gravitation. Last thing for review of topics. And then we'll get to the more interesting practice stuff. circular motion. So we started with this issue in circular motion that if we draw this object that's going around in a circle, we know that at one moment it has a velocity that points kind of up and to the left. If we look at it some moment later, its velocity points kind of down and to the left. Down here, our velocity points to the right. So we know that our velocity vector, since we have to account for both speed and direction, it's changing there. So we know we're accelerating, but if we have an object going at constant speed, and we look for the acceleration, we would have, in the past, done something like acceleration equals v minus v naught over t. We'd have the same numbers for v and v naught. So we get acceleration as 0, but we know it's not 0 because it's changing direction. So luckily, somebody else has done this very clever geometry for us and figured out that if we're looking for acceleration toward the center of the circle, we can calculate that as acceleration. We give it a subscript c for circular or centripetal, that's really what it means, center-seeking acceleration, is equal to the speed squared divided by the radius of the circle. Now, if we have an object that's going around in a circle, there must be some force that's causing it to go around in a circle. So it'll probably make sense for us to look at forces. Anytime we do forces, we can do Newton's laws. So we can write acceleration equals net force divided by mass. This time, instead of looking in the x direction or the y direction, we look in the c direction, the centripetal direction, where toward the center of the circle is positive. And since we have this expression for centripetal acceleration, we can plug that in here. And so the form of Newton's second law that we're used to working with for circular motion is v squared over r equals net centripetal force divided by mass. Or sometimes people multiply both sides by m, so it's mv squared over r equals net centripetal force. Now this net force here, that's not a force. There is no such thing as the centripetal force. And I think we kind of get used to that terminology before we study physics, except people use the term centrifugal force, like a force that flings something outward from the center of the circle. Here it's not, that's the wrong direction, first off. If we were being pushed away from this circle, not only would we not go around in a circle, we'd be not even going in a straight line, we'd be curving outward away from the circle. So to have this thing curving in this direction, we have to have a force inward toward the center of the circle. That's center-seeking, not center-fleeing. Centripetal, not centrifugal. Fugal means flee. So we're talking about centripetal forces with an S, plural. We could have multiple forces toward the center of the circle. Might be a tension force, might be a gravitational force, might be a normal force, might be a frictional force. But it's not centripetal force. It's a force in the centripetal direction, but it's not a new type of force that we have to worry about. So any of the forces that we've talked about so far can act in that direction. And so our next step here would be to replace this net centripetal force term with the sum of all forces that have some component in that direction toward the center of the circle. Believe it or not, the power or the PDF just popped up, so switch over to that. Now with circular motion, and again later with rotation, we found that sometimes it's useful not to work with linear quantities like speed, velocity, and acceleration. Linear, sorry, I said speed, but I meant distance, position, speed and velocity, or acceleration. So not x, v, and a, but angular versions of those quantities. So not how far in meters around the circle have we gone, but how far in degrees or in radians around the circle have we gone. Not how many meters per second are we traveling, but how many radians or how many degrees per second are we traveling around this circle. So we have this, these two systems to describe those quantities, the linear system and the angular system. Now, the relationship between those is really just the definition for radians. That's the system that we're going to use here, not degrees, but radians. It's really just the definition for radians. A radian is the angle that you would cover on the outside of a circle if you went one radius around the circle. So we take a circle that has a radius of 1 meter. It has a circumference of 2 pi r, so about 6.3 meters. If I walked around 1 meter of that 6.3 meters, the angle that I've traveled through is 1 radian. Traveled 1 radius distance around the outside, I traveled 1 radian angle around the circle. So this relationship reflects that the angle times the radius in meters gets us the linear distance. The angular velocity times the radius gets us the linear velocity. The angular acceleration times the radius gets us the linear acceleration. In this case, we've got VT and AT written here. It stands for tangential, just so we don't get it confused with centripetal. Tangential means around the circle or along the edge of the circle, not in or out, away from the center of the circle, but around the outside. So some of these problems, though, maybe give you radians per second instead of meters per second when you have to do this calculation. And that's fine, we can handle that. We just need to do the, use this equation to find that relationship. Now, these equations aren't on your green sheets. So I suspect that that means they're just expecting you to know what radians per second means. And know that if you went 2 pi radians per second, that'd be 1 complete revolution around the circle every second. And if you knew the radius of the circle, you could figure out how far that was. So if it's 1 meter times 2 pi to get circumference, it'd be about 6.3 meters. So 2 pi radians per second would be the same as 6.3 meters per second. I think they're just expecting you to be able to rationalize your way through that. If you're not there, if that doesn't make sense to you, if everything I've been saying so far about radians and linear quantities and relationships makes no sense to you, just memorize these equations and you'll be good.
Could you make it a little clearer? It's kind of fuzzy on this end.
Visually?
Yeah.
Okay, I can try here. I got a pinwheel. Is that any better, Katie?
Yeah.
Okay. It's highlighted now, so you know it's important. Probably a good idea to know the names for these things too, and the variables that we use for them. We've got theta for angular position, omega for the angular velocity, and alpha for angular acceleration. And then the units are going to be useful for you as well. Radians, radians per second, and radians per second squared. The angular systems here, if you look on your green sheets about halfway down, you've got equations like theta equals theta naught plus omega naught t plus 1/2 alpha t squared. So those are the same as the kinematics equations, just all the linear quantities have been replaced by angular quantities. So you might work in that system as well. Questions on those? Okay. Second law we talked about. checked out a second computer from the library today to make things easier. I'm really happy with it so far. All right, we talked about that. Well, that brings us to gravity. The law of universal gravitation, in words, says that every object attracts every other object in the universe, every single one. And that the strength of that attraction is proportional to their masses and inversely proportional to the square of the distance between them. Proportional means we can multiply by some constant. The constant here is capital G. The number for that's on your green sheets. 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared, or maybe the units on that. That's the universal gravitational constant. As far as we can tell, it works everywhere in the universe. Everything attracts everything else. Now, we use this equation primarily when we need to look at orbit, at least in this class. We're primarily going to look at this equation when we want to talk about orbit. Orbit is really, it's elliptical motion, but basically it's circular motion caused by a gravitational force. So we take these two separate ideas, gravity and what things do when they go around in a circle, and we combine them and we can get these rules for gravitation. And I didn't write more about that on the slide, so I want to do that here. These are equations that aren't given to you on the green sheets. So again, they're going to expect you, I wouldn't think they expect you to memorize these, but they expect you to be able to combine these two things. So if we have circular motion, we can write v squared over r equals net force in the centripetal direction times mass. And let's say here we're talking about a little tiny mass going around a really big mass. So like a spaceship going around the Earth. It's a little tough to tell because of the scale, but I've used a capital M and a lowercase m to denote those. So my force toward the center of the circle, then, I could write with that gravitational force equation, the law of universal gravitation. So I write that as v squared over r equals g m1 m2 over r squared divided by m. So I've just replaced the net force term with this gravitational force term. And then we need to clarify our m's a little here because we're working in a few different systems. The two m's that we're dealing with are the little mass and the big mass. And then in this equation, the Newton's third law equation, or sorry, Newton's second law equation, the mass we're talking about is the mass of the thing that's going around in the circle. So the little thing is going around in the circle here. So let's substitute, let's see, g little m big M over r squared divided by little m. And then we see, the little m's cancel. And if I multiply both sides by r, I get one factor of r canceling. And then I get v squared is equal to g big M over r. We want to have some object in orbit around some other object, the big object having mass big M, then we can have that orbit only if this relationship is true. If r, which is the distance from the middle of the big object to the middle of the little object, and v here is the speed at which we go around the circle. If that relationship isn't true, then either our thing that's supposed to be orbiting is actually spiraling in and going to crash on the surface, or it's spiraling out, maybe very rapidly, maybe very slowly, away from the big mass. So it's not going around in a circle anymore, it's doing this kind of spiral shape. Now we also can do a little bit with time here. How much time does it take to go around once? Well, we've got a speed. If we knew the distance that it goes, we could figure out time from there. Well, look at this object. The distance the little m goes, that's a rough circle. The distance that little object goes, and this is radius r, the distance here is going to be 2 pi r. So then if we use speed equals distance over time, where speed is square root gm over r, equals the distance, 2 pi r, divided by the time. That's a not very well arranged equation to find time. So you can isolate time from there. That's just algebra, though. The physics is done at this point. So we can isolate time and figure out what's the orbital period, is the name for that. The time to go around that circle one time to make one orbit. This equation and this equation both are not given to you on the equation sheet. They give you the circular motion equation, sort of. They give it to you in 2 steps. Newton's second law, they give to you, and then they give you the equation for centripetal acceleration. So we have to combine those two. And then we have to recognize, this circular motion is happening because of gravitation, and so we stick the gravitational force equation in for the total force. So really, either of these is a combination of at least 3 equations. This one is 4 equations to get to it. They really require that we understand how a large number of pieces fit together in order to solve what seems like a fairly simple problem at the outset. Something like, how long does it take the moon to go around the Earth? It's about 29 days, if you didn't know. If they ask you that one, just put down 29 days. I've seen a calendar, I know. Evidence? Google Calendar says so. It's how often I turn into a werewolf. Whatever you want to use for your evidence. All right, and the last thing. Here we go. Gravitational field. Sorry, it's not showing up. Let's see, maybe it wants to scroll up for us this time. It does. Gravitational field, little g. Wait a minute, isn't little g the variable we use for acceleration due to gravity? It is. Not coincidentally. They'll have the same value. In fact, we've even used this equation. We've rearranged it as Fg equals m times g, but it's the same equation. That little g we had been just calling the acceleration due to gravity, but it's really also the magnitude of the gravitational field. The idea of a field in general is something that they really stress on the AP stuff. We have these. I used to have a list posted on the wall, and I don't know what happened to it, so I'm totally disoriented now. Yeah, it's nowhere. Okay. Well, they can't see it on the video, so watch this. We have this list right here, right, guys? See? See? It's right up here. Hear a lot of yeses. There's some head nodding, too, but it's not on the video. We have this list of the 7 big ideas in physics. We only have to know 6 of them for this class. Sweet. 7 big ideas for physics, 6 for this class. One of those is that basically fields are a thing. Fields exist. 1/6 of what they want you to know about physics is that fields exist and they have all these consequences. The idea of a field is that really these 2 objects that have mass, they don't pull on each other. There is no force directly between those 2. Instead, because I place an object that has mass into space in this universe, it somehow changes the space around it. It changes it in a way that anything else that has mass notices. The analogy that everybody uses for this, because it's a good one, is the trampoline thing. Put a bowling ball on the trampoline. Just let it sit there. We're not like bouncing the bowling ball on the trampoline. It's probably dangerous, but just let it sit there so the trampoline sags in the middle. We get to see that the trampoline is sagging in the middle, but say you're an ant on the trampoline and you have really lousy distance vision. You know, you're a nearsighted ant on a trampoline. This is getting abstract fast, but say you're a nearsighted ant on a trampoline that somebody has put a bowling ball on. We've all been there, right? And you can't see the bowling ball. You can't even see that the thing you're on has changed shape, but all of a sudden you recognize, man, it's a lot harder to walk that way than it is to walk this way. We can't perceive that change directly, but we feel an effect from it. Somehow we can tell that the surface we're on is different than it was a minute ago. And if we, ask a passing grasshopper what's going on, he might be able to shed a little more light on this. Probably not, though. Grasshoppers are jerks. We all saw ants, right?
Yeah.
Or Bug's Life? Which one were the grasshoppers jerks? Bug's Life. Okay, yeah. So the same thing happens, sort of. It's a three-dimensional versus a two-dimensional idea, so it's tough to picture. But the same thing happens in space. You put an object somewhere in space, something that has mass, and it changes the space around it in a way that we can't see, but we can detect. Because if we put something else that has mass in it, that has mass near it, it's pretty easy to move that thing toward the other thing and pretty hard to move it away from it. In fact, if we just let it sit there, it starts to move all on its own toward that other mass. Almost like it's rolling downhill across that trampoline. But the space is different even if we don't put another object there. It's not a direct force. It's that one mass changes space, and then that change in space gets detected by the other mass as acceleration. Now, how do we know it happens? Because there's a time lag. Now, you have to get into a really specialized experiment to be able to notice this. So let's just imagine a situation where the sun disappears. It takes some time before we notice here on Earth for two reasons. One, because light takes time to travel through space. That's actually a field also, but it's a field we don't talk about until Physics 2. It takes light some time to reach us, so before we can tell that the sun is gone in the sky, we still have to have all the light that left the sun while it still existed get to our eyes. It takes about 8 minutes to get from the sun to the Earth for light. So we don't notice visually for another 8 minutes. We also don't notice in terms of Earth's orbit. We continue orbiting the sun for 8 minutes after the sun no longer exists in this weird model where the sun can just wink out of existence. We think of that as almost a wave in space. So if we took that bowling ball off and we were really quick about it, we could actually take the bowling ball off faster than the trampoline springs back to its original position. It takes some amount of time for that to go. And if we're really fast with the bowling ball, we can actually see bowling ball is not on the trampoline. Trampoline is still deformed. It springs up pretty fast. You probably need like a high-speed camera to see that, but the same thing happens in space. So we have some good evidence for this idea that fields exist. The strength of that field is just a ratio. The idea is if we had some object that we were going to use as our tester object with some mass, the fact that it has mass means it works as a tester object. Anything that has mass can detect this field. We put some object that has mass in this space, we figure out how much force it experiences. If we doubled the mass of that object, we figure out how much force it experiences, its gravitational force. we find there's this constant ratio. Even if we're not close to the surface of the Earth, anywhere in the universe, if we set up some arrangement of masses and we put our test mass there, figure out how much force it has, and then put a different mass in there and figure out how much force that one gets, we get this constant ratio. And it's that ratio that we're talking about for the strength of the gravitational field. It's this space has this much of an effect, this many newtons of force for every kilogram of matter that we put here. 9.8 newtons per kilogram is the gravitational field strength here on the Earth. So for every kilogram of mass you have, you feel 9.8 newtons of force. Now you accelerate as a result of your force and your mass as well. So it turns out that for every kilogram of mass you have, you get more force, but for every kilogram of mass you have, you get less acceleration. So those two balance each other out. So it doesn't matter how much mass you have, you accelerate at the same rate. Or we express that as we have the same gravitational field for all of us. Questions on gravitational fields? Nearsighted ant on a trampoline. I had to write that one down.